It's 9:05. Let's get started. Hello, everybody. My name is Bartek Nowierski. I am a lead in the Tokyo office at Google. And together with Benoit from the Paris office and my team, we work on a project called PartitionAlloc Everywhere. PartitionAlloc is Chrome's own memory allocator. It was introduced originally in Blink long time ago. And to access it, one would have to call allocation and freeing functions directly. Now, here's a pop quiz for you. Does anybody know where the name PartitionAlloc came from? I don't see any hands in the air, so here's the answer for you. It was originally, well, for security reasons, we provided the functionality to split into partitions and mainly to isolate certain critical types to minimize chances of type confusion attacks. Blink has a couple buffer partitions. It has a layout partition, which will probably go away soon as we're about to alpinize it. And it also has a fast malloc partition. Now, the last one was not created for security purposes. It's a kind of like catch-it-all partition anyway. It was created because somebody realized that apparently PartitionAlloc performs better than a system allocator. So with that observations, can we have it everywhere? Well, yeah, we can, and performance is only one of possible reasons to have it. And to be honest, at first we didn't exactly know how it would behave for generic workloads in entire Chrome, so we didn't know if performance would go up or down. There was a little bit of a risk there, but we took it. Another reason would be to reduce the complexity of the code, which would no longer have to deal with so many different allocators in the code base. Security would be another reason, but to be honest, none of those were really the drops that made the cup run over. What made it is when we started talking about Miracle Pointer and star scan support. These are technologies that I spoke about in the previous BlinkOn that are meant to mitigate use after free security issues. And they require to have our own allocator to work. And that was the reason why we decided to finally pull the trigger on PartitionAlloc everywhere. So we know why. Now, how? Are we supposed to search and replace tens of thousands of locations where we call malloc? Well, not really. There is an already existing infrastructure to replace malloc and free and a whole shebang of memory management functions, and it works differently on every platform, but the functionality exists, and it's been successfully used by other allocators. So we didn't really reinvent the wheel here. But nonetheless, we had to make some work to adjust PartitionAlloc to the new environment. For example, we had to make sure that PA initializes itself before the first allocation, which sounds trivial, but it really wasn't. Note that the first allocation comes way before the main function is called, and we cannot really rely on the order of initializers in C++. Another thing is that we had to make sure that the allocator doesn't allocate itself. Previously, it was just fine, because when we only supported Blink, we could call malloc from the allocator, and it will go into the system allocator. Right now, when we intercept malloc ourselves, obviously PartitionAlloc cannot call malloc because we'll loop on ourselves. All right, there's a long list of other things that we had to do, but I'll spare you the details on this for now. So we're making it happen. We shipped Windows 64-bit and Android support in M89. Windows 32-bit and Linux followed shortly after in M90. Regrettably, as we speak, we're pulling out the Linux support in M99, M91, but we're very hopeful that we can bring it back in M92. Fingers crossed. In parallel, we're working on Chrome OS and macOS support, and maybe, just maybe, I'll have some good news for you in M93, but don't quote me on that, no promises. Now, one might ask a question, why are we doing those one by one? Why can't we all do them all together? Well, each platform is different, like different way of intercepting, different unspecified, undocumented behaviors, and different surprises. So each of those takes significant amount of time. That's why we have to do them like milestone by milestone. But we're getting there. The goal is to have PartitionAlloc everywhere, everywhere. Let's talk about what PartitionAlloc everywhere brings to the table. Well, we got really good memory improvements with no performance cost. So on Windows, we get up to 22% memory savings in the browser process, a bit less in the render process, only 8%, and for Android it's 8 and 4, which is not as good, but hey, we'll take it. In terms of responsiveness, we reduced junk by 9% in 64-bit and 4% on Android. Scroll latency reduced quite a little bit too. Now, keep in mind that this is data from an A/B experiment in a dev channel in M89. So the question was, do those memory savings are those memory savings preserved in a stable channel? And the answer is yes. This graph presents relative memory usage, and up to here, the M88 binary was dominating the world, and here is when we released M89. And you can see very clearly a sharp drop of about 20-ish%. So that confirms our data from dev. Now, keep in mind that in this chart, what you're seeing is not a A/B experiment that isolates this particular feature, but you're seeing the entire work that happened in Chrome between 88 and 99. So this drop can also be attributed to possible other improvements in the browser, but in reality, it's mostly us. We continued working on PartitionAlloc, on improving PartitionAlloc performance, and we repeated the dev experiment in M92. And look at that, we got 30% memory improvement on Windows 64 and 17% less junk. So numbers improved quite a bit since M89. And on Windows 32-bit, we've got 22% less junk. Other metrics improved nicely as well. How are we doing on time? Oh, right. I gotta skip that slide for the sake of presentation flow. Okay, let's talk business. So, architecture. PartitionAlloc, in a nutshell, can be perceived as a combination of a couple of components. So one would be the central allocator, which is guarded by the pair partition lock. And because locks are bad, we implemented a layer on top of it of thread caches, one per each thread, that instead of locking, they use thread local storage access, which is much faster. Here's how the central allocator looks like. I apologize for a very ugly drawing, and I promise I will never ever draw again. But anyway, this is probably the least interesting slide of the presentation, and for sake of time, I'm going to skip it. But feel free to go back to learn more details of how things work inside PartitionAlloc. Thread cache is a bit more interesting. So, like I said, there's one central allocator lock to rule them all per partition, which could obviously lead to a contention, which obviously would increase the cost of memory allocations and allocations. One possible solution would be to split PartitionAlloc into more partitions, since the lock is per partition. But that would actually increase the fragmentation and would cause more memory usage. So we don't want it. We want to come up with a simplest, smallest possible solution that still has a decent performance. And we think that per thread cache was a great choice for that. It's lock-free. It stores a list of free slots ready to be grabbed by a thread in a thread local storage. And obviously, since it's cache, it increases memory usage. As I said, increasing memory usage is not good, but empirically we figure out it costs us only between 200 and 700 kilobytes per process, which is something we can live with. And with that little of a memory investment, we got an amazing cache hit rate of over 95%. This makes us look pretty good on speedometer benchmarks, where we're on par or better on all tested platforms so far. In contrast, before we implemented thread cache, we actually regressed in some platforms, not by much. I think it was in order of like 1-ish, maybe 2% on Linux. It was just enough for us to invest time to look into this and fix the problem. Now, like I mentioned, over 95% of allocations are coming from thread cache. So we have to make sure we don't do anything stupid there, because it's a performance critical hot path. So we cannot add some random if branches. We cannot access some deep structures that are likely not in cache. We also have to be careful when fetching more free slots from a central allocator, so that we don't lock every single time we do it. Like, the idea is to avoid locking. So we batch the request, we grab the log once and fill half of the, or a certain amount of thread cache all at once under one log acquisition. We also fine-tuned thread cache specifically for Chrome usage. So after analyzing the Blink usage patterns, or specifically V8, we realized that it allocates larger amounts of memory than we typically cache. So we had to increase the thresholds, but specifically we limited it to only 4 ground renderer process. Obviously, it eats more memory in this process, but it's faster. It's significantly faster. To counteract increasing memory, we also make sure that we get idle threads to purge their caches as soon as possible to avoid stranding memory for too long. All right, time for some anecdotes. I'd like to share our experiences from developing PartitionAlloc everywhere. So let's start with static local variables. What could possibly go wrong there? Well, starting with C++11, static local variable initialization has to be thread safe, so we have to lock. Now, the sequence of events can be as follows. On the process initialization, CRT initializes, it allocates, which triggers PartitionAlloc initialization on the first allocation, which used to use static local variables, which, as I said, has to log. In case of on Windows, it would try to acquire a critical section, so it calls back to CRT, which is not yet initialized. Bum, bad things happen. So we got an easy fix for that. As you can see, this one line got replaced with a little bit more than one line, which essentially reinvents the wheel and implements the static local variable support with our own log support. Now, as easy as it may look, we got that wrong, and that's a homework for you. If you're curious, find a bug. Good luck and have fun. There are actually 2 bugs in this code, but I don't think you'll be able to find one without more context. But one should be within reach for everybody. Well, here's another one. That's actually funny. When trying to format a floating point that's more than 30 characters long, it calls AspirinF, which allocates. And that will be fine, except that on Android, it actually results in calling the system.alloc, which is not intercepted by PartitionAlloc. But the pointer was, the return pointer was passed later to the free that was intercepted by PartitionAlloc. And if we were asked to free the memory that we didn't allocate, bad things can happen. So the solution was to implement our own AspirinF and substitute it at link time. We actually broke our teeth on a similar issues with strdupe and getCWD before. So we're kind of like scratching our heads and wondering like how many of those issues are still lurking and waiting for us out there. But I hope we got the last one. The AspirinF one actually almost blocked us from shipping. We got it like very late in the beta. Another one. Do we have time? Oh yeah, we still got a minute or two. Another one is glibc. Old glibc had a bug. It used an internal function to allocate, which was not intercepted by PA, an external 1 to 3, which was intercepted by PA. And as you already know, if you try to free something you didn't allocate, bad things can happen. Now, this one is embarrassing. We're supposed to be the technology that enables anti-UAF techniques. UAF stands for use after free. And we actually did a good job causing a UAF in the allocator ourselves. So when an allocation happens during a thread destruction, the thread cache structures would get already freed, but later on we actually still access them. So for quite some time we actually managed to use those without a crash, but at one point of time after a refactor we hit the crash. That's how we found out about the issue. Here's some reading for you if you'd like to learn more about PartitionAlloc. Any questions from the room?
How did you solve that issue with thread destruction?
So I wasn't the one solving it, so I would suggest that you click on the link in the presentation, which has the fix. Sorry, I cannot be more specific.
Yeah, I had a question in the Q&A section, but I'll just ask it live. So my question is, why is PartitionAlloc so much better than these other allocators, at least apparently? Like, presumably people have spent a very long time optimizing the allocators on these platforms. So what makes PA so great? Like, does Chrome just have very unique workflows? And if it's not just Chrome being special, should platforms consider adopting PA as well?
That's actually a really good question. Like, I don't have like a really solid answer for you on this one. There's definitely definitely the simplicity of it helps. It's a like a simple slab-based allocator. It's like pre-reserves like stripes of memory, and like groups them by sizes and just commits memory as needed. Why we got so much better results than other allocators with just that, I'm not perfectly sure. It's been well, probably before I joined the team, it's been tuned for Chrome usage in some cases, but like me specifically, I don't see many cases where like where the code is very Chrome specific. So we're actually talking about making it into a standalone library and letting others use it as well. Sorry, I've been slacking on reading your comments, so let me do this now. Yeah, somebody wrote a comment. Oh, Kantaro wrote a comment that originally it was called CTMalloc from the names of the authors, but it was confused with TCMalloc, so it was renamed.
Yeah, and also, so I would emphasize that the PartitionAlloc is extremely optimized for the committed memory. So we are really minimizing the amount of the committed memory. So by really proactive about decommitting, so what is not used. So yes, I think we are doing very smart thing. So that's why we are doing better.
Somebody made a comment that system allocators were tuned ages ago, and that could, yeah, that could be it. Like, we're dealing with the old code that has been with us for tens of years. All right, are there any more questions? We have literally 1 more minute left on the clock.
Maybe I'll ask one. Why is the cache so good? I mean, what do you presumably in the cache you can only put a fraction of the allocation. So why exactly does it help so much? Do you understand that?
Yes.
Okay, cool.
So why is the cache so good? Why is the thread cache so good? So essentially, like well, the key is like from not having to take the log. TLS access is much faster than taking a log and avoids any contention. So if we can just like prepare a bunch of free slots that are ready to grab in the cache, the app can just like grab one by one, and once we go beyond a certain threshold, then we take the log once, we get a bunch of new free slots into the cache and release the lock. By doing so, we also increase the cache locality, so that can play a role there as well.
Okay.
All right, it's 9:30, so thank you everybody for attending and have an amazing day. Don't forget to smile.